Hey class, Adam Ward here. I want to talk to you today about feedback systems of CSTRs. This goes along with Lecture 6 in your textbook, Chopra Lecture 6. Okay, so you should have already watched a video from me about feed-forward systems where we let mass move in the downstream direction. And so we started with a system that looked pretty much identical to what I've drawn here. And with feedback systems, we're just going to add one new wrinkle. That new wrinkle being mass is going to move both ways. So now mass can flow from 1 to 2 as well as 2 to 1. You'll see I've added in red here Q21, so a term that just advectively moving mass the other way in the system. And so my hope by this point is that you're quite comfortable writing out these mass balance equations, both for CSTR number 1 and CSTR number 2. And you'll notice in these two equations that what I've highlighted in red pen are the new terms that arise because of that Q21. It forms a load to CSTR number 1, and it forms a sink or removal term for number 2. Right? So highlighted in blue there so you can see that connectivity between these two systems. Now, in the past, with a feed-forward only system, you could just solve that in serial order, meaning you could solve lake number 1, you would know the concentration in 1, then you could solve 2, you would know the concentration for 2, and you could solve 3, and so you could work your way down the system. What makes this a little bit more challenging now is that the upstream concentrations depend on the downstream ones, so they are interdependent on one another. That means we can't solve these equations separately, we've got to solve them simultaneously. So I want to talk about first the steady state simplification, what if dc dt is equal to 0. And so from the two equations on the previous slide, I'd like you to practice a little bit of algebra and see if you can zero out that dc dt term and end up with two equations that look something like this. And so the idea here is that you've got the concentrations, C1 and C2, and you're grouping together and factoring out of that equation everything that's multiplied by them, and putting the loads on the right-hand side. And so if you've done this correctly, you should have the four terms that I'm writing out on the right-hand side here. You'll have A11 and A12, so that's CSTR1 and CSTR1, excuse me. And then for CSTR number 2, you should have A21 and A22. So if you can't manipulate the two previous equations into looking like these factored out forms, that's something that you need to practice. Assuming that you're with me, let's talk about what these terms are. And so just like in the previous video where we talked about these lambdas that related loads in one lake into concentrations in another, here these are actually formulated as assimilation factors. How is a load from X acted on by Y? So A21 is asking, how is a load from 2 acted on by lake number 1? Well, these are assimilation factors, just like we've seen before in this class. One common question that people have then is, wait a minute, I've got A's, I've got lambdas, what is the difference? It's just whether or not you divided by volume. So when you zero out that dc dt term, you don't necessarily have to have divided by volume there. It would just drop out because it's volume times 0. So lambdas and A's, the only difference is that one is normalized by volume and one is not. Now, our strategy for solving these equations simultaneously has to be a little bit more sophisticated than just doing them one at a time, because that's impossible. And so we're going to solve these using matrices. If you haven't had matrix math before, that's okay. I'll tell you what you need to know. The idea here is that we're going to have a matrix that's got all of the assimilation factors multiplied by concentrations, and that's going to equal a W. Right? And so this should look very parallel to what we did in lecture 1 in this class, where assimilation factor times concentration equals loading. A times C equals W. Now for our two equations that we're working through with this lecture, those matrices would look something like this. Now, one quick reminder on matrix math. If you were trying to solve this for concentrations and these were just variables, you would divide by A. So you can see I've written that out in black pen for you. Concentration would be W over A. when we're doing matrix math, we don't do exactly that. Instead, we multiply both sides by the inverse of the A matrix. Taking the inverse of a matrix is sort of the equivalent of taking 1 over A and multiplying both sides of an equation by 1 over A. And so our strategy here is going to be to multiply the inverse of A times that vector of loads. And this assumes in this scenario that the loads are what you know, the assimilation factors are what you know, and the concentrations are what you're trying to find. Haven't done matrix multiplication, haven't done matrix inversion, no problem. With your homework assignment, I've got a couple of different tools that I've used. There are some websites that are great. You just tell it how big the matrix is, you type in the numbers, it will do the inversion, it will do a matrix multiplication for you. You can do this on many of your calculators. TI-82s and higher, I believe, can do matrix multiplication. You could do this in MATLAB or R or Python or your favorite mathematics program if you have one. So one thing I want to just point out to you all here is this matrix of assimilation factors. Right? What is this? These are the system characteristics. This is a matrix of all of the coefficients that describe flows, reaction rates, settling rates, and help translate loads into concentrations based on that system behavior. I'd like to talk to you one more slide here about that A matrix, the assimilation factors. And so let's imagine we're working on a much larger system. And so we've got quite a big matrix here. Now, along the diagonal rest all the terms that we had when we were working on just one CSTR. Right? This is the effect of a direct load into a lake. So A22, that describes how loads into 2 are related to concentrations in 2. So if you only had if you were trying to solve a system of non-interacting CSTRs, you might only have terms along that diagonal. In blue, I'm showing you the terms on the subdiagonal. And on the subdiagonal, we're looking at how upstream loads affect downstream concentrations. And so that's fundamentally the feed-forward system of the portion of the equations. In green, above the diagonal, is called the superdiagonal. And this is how downstream loads affect upstream concentrations. That's where we've added this lecture, is these feedback terms. So A23 is asking how loads into 3 affect the concentration in 2. So this feedback diagonal is what lets downstream lakes communicate with upstream systems as we solve this set of equations. Okay, so what should you be able to do at this point? You should know what feedback systems are. You should understand how they change your mass balance equations, how they simplify equations, and you should be able to describe, at least conceptually, how we use matrices to take equations, turn them into matrices of coefficients, and how we go about solving them. That's something we'll practice in class as well as in your homework. Thanks for sticking with me, class.